Here now there's a decision maker, Monsieur Gérard Mousse. This is the manager, the French manager of the operation. The objective is to increase profits. Okay? We would like to increase our profits. What's the performance measure? Well, it's revenue minus total cost. So the relevance of the case is how we compute the total cost. Yeter artık ya, lütfen. We assume that any extra amount of product we can produce, mushrooms, can be sold at the current prices, so the revenue can be computed very easily. The question is what are the total costs? The decision criterion is to maximize profits. The alternative courses of action, that is the decision variable that we need to consider, is the number of flushes in each cycle. I remembered when I mentioned 45 days in my case, I remembered it wrong. The 45 days was the entire lifetime of the compost. At the end of 28 days, the compost started to produce mushrooms, and after several cycles, at the end of 45 days, there were no mushrooms left. Huh? That's something like that. And the context of the problem, I mean the background, what we mean by the problem context here, what is the wider system and what is the narrow system of interest, is as defined by our boundary judgments. Now here is an influence diagram. This is good. I like this example. It's a good example for an influence diagram. For this case, again, you can study this in your own time, but we can make a few comments. As you remember that on the top, what should be placed at the top of the diagram? What is the first item to place? When you are constructing an influence diagram, right? You start with a blank page. Huh? At the top, you first put the first item. What is it going to be? Didn't you do any exercises on influence diagrams? It is the unknown that you would like to know. Huh? You start with what you want to solve. You start with the solution that the model will tell you. What are we trying to discover in this exercise? The optimal number of flushes, right? Currently, they are using 5 flushes, but the idea is maybe if you reduce the number of flushes from 5 to 4, maybe, or maybe to 3, or maybe to 2, it might be possible that we shall be able to increase our total production, in which case we shall be able to make extra profits. Okay, this is the case. The problem that we address is this. So the unknown is the number of flushes. You write it at the top of the influence diagram. You see the square or the rectangle over there at the top. It says number of flushes per cycle. This is the unknown that you are trying to determine. The model will give you the answer, will give you as the answer this information. So you start with the optimal solution that you would like to calculate. Once you know it, what else can you determine? Huh? And it goes on like that. For example, if I know the number of flushes per cycle, let me try to use this highlighter if I can. If I know this, if I know the number of flushes per cycle, and also if I know the duration of the growing phase, what does this mean? How long will it take? How many days between each flush that I have to wait, the growing phase? If I know that, then I can compute using this information and this information, I can compute the cycle length, as you can see. Also the flush times, sorry. Okay, duration of growing phase is once you put the seeds, the spores, you have to wait for 26 to 28 days, remember? And until the mushrooms start to grow. And then when you take the first flush, you have to wait for as long as what it calls the flush time to get the second flush. And then you have to wait another flush time to get the third flush, etc. So when those three pieces of information are given, then you can compute the cycle length. Right? It's just arithmetic. Number of flushes per cycle, let's assume that it is 5. In one cycle, I will collect 5 flushes. I know that before I can collect these 5 flushes, I will have to wait for the duration of the growing phase, which is 26 days. And each flush takes, let's say, 4 days. 4 times 5 is 20 days, another 26 days to wait for the mushrooms to grow, which gives me 46 days, which is the cycle length. Once I know the cycle length, I can compute how many cycles will be available in 1 year. Since one cycle takes 46 days, let us say, 365 divided by 46 will give me the number of cycles per year. Then in each cycle, I know I use this information that the trays per cycle, how many trays are available for me, and how many sheds are available. I think 66 sheds and 44 trays per shed are available. Using these numbers and the number of cycles per year, I can compute how many trays of mushroom I can grow in 1 year, etc. So one information is used subsequently to obtain another information. If I compute, for example, therefore, the number of trays of mushrooms that I will be able to grow in 1 year, I can then compute, in number 6 here, the annual tray preparation costs. I know, for example, that there will be 2,520 trays of mushrooms, so I will have to incur a cost for preparation of each of these 2,500, I don't know the exact number, I'm just making up the number, of trays. So that gives me the opportunity to compute the annual tray preparation cost. In similar way, you can follow the other links, and then, of course, this cost, where is my, okay, this cost is now taken here and added. Where is the total cost? Well, the total cost is not indicated. I mean, we could also include a circle for the total cost and collect them there. Instead, what it does in number 14 is it takes the total product, additional product, multiplies it by the selling price, and subtracts all the cost items. The first cost item that I have indicated in yellow is the annual tray preparation cost. The second one is computed in number 7, as you can see. Let me change the color. Where is it? Well, anyway, in number 7, you have the annual tray loading and unloading costs. Then there are compost revenue, which is the income, annual picking costs, etc. So all of those are computed either by using the information you have already computed before or using data coming from clouds from the outside. You know, these cloud shapes are for data. The circles are for what you compute. The rectangle at the top is what you would like to compute as a result or determine as a result, and the ellipse at the end is your objective function. So this is a good example of an influence diagram. As I said, you should make sure that how the costs, what sort of different costs. The point of this case exercise is to point out how many different types of costs can occur in such a mushroom growing facility, for example. Several of you not all of you, I know not all of you, but several of you will take jobs in production institutions, companies, where they produce manufacturing or something like that, manufacturing companies, in which you will have a similar situation. There are many, many, many cost items. Remember I said that being able to understand cost is extremely important for your careers. In such complicated situations, each cost item must be considered, and the correct value of that has to be computed. Otherwise, you won't know. For example, changing the number of flushes is very, very important. I know this from my own experience. The number of flushes will make a real difference in your total operating profits. So in order to be able to find the correct number, you have to consider all the cost implications very, very thoroughly and correctly. So costs are really very, very important. And this example illustrates all sorts of costs in great detail. Now these are listed here. I scanned these from the textbook, but when scanning some word recognition algorithm, some mistakes are introduced. Okay, so it's not L tray, it is proportional per tray, etc. Anyway, the correct values are in your book. So this is a list of all, for example, raw materials in the compost and tray preparation. So there are many, many sections. In one section, they only prepare the compost. Compost is raw material. It costs. This compost is bought from nearby farms. In farms, as you know, there are animals and there's harvesting, etc., and there is usually waste material. This waste material is the material for preparing compost, saman mesela, or straws and things like that. You use them to make trays perhaps, or use as a compost. So raw materials for preparing the compost. Is it relevant? Yes, of course it is relevant. It is a relevant cost because the amount of, so is it fixed or what? Nature of effect? It is proportional. Proportional to the number of trays. It is proportional per tray. There's a misprint over there. So what will it be? It will be an input to the preparation cost per tray, etc. So electricity, for example. Is it relevant? Yes, because electricity is used in the sheds, especially. Kırmızı bir ışık kullanıyorlar böyle karanlıkta görebilmek için. And in other places for heating purposes, etc. Again, it is a variable cost per tray. Diesel fuel is used for trucks and lorries, which they use in their facility for carrying and handling or maybe there are forklifts and things like that. Yani mazot kullanan vasıtalar. So maintenance on vehicles, is it a relevant cost? It is a relevant cost. But vehicle depreciation, it's not a relevant cost. Maintenance of the yards and the buildings. The yard is the area, the open area in the facility, and there are buildings. And there you have to pay for maintenance of these places. Is this a relevant cost? No. If you do not change the number of flushes, this cost is going to be still incurred. If you change the flushes, again, the same cost is going to be incurred for the maintenance of the buildings and the yards. Changing the number of flushes does not change the maintenance costs. Remember the definition of the relevant cost. The relevant cost is the cost which changes with your decision variable. If your decision variables change and the cost does not change, that cost is irrelevant. Okay, like depreciation. So you can study, this is a long list, I have scanned it all, but I'm not going to Some of these are, for example, sunk costs. Some of them are variable. Some of them are fixed. Constant means fixed, obviously. And you can study this carefully in your own time. The salaries, for example, salary of Marchand, whoever he is, the names are mentioned in the case. There are some people. Her salary, for example, is not relevant. It's a constant. I mean, changing the number of flushes will not change the expenses for paying this person, the salary of the person. So many, you see, costs are not relevant in this, on this page. Then we construct a mathematical model to find out the optimal value of the number of flushes. It's not necessary for me to explain all the mathematics. You can again see it. But what I want to point out in this, for this case, and also for the LOD case, is that the models that you see here are spreadsheet models. Huh? The solutions are obtained by what? By enumeration, right? I mean, we obtain the solution to the LOD problem in two stages. The first stage was obtained by analysis, by calculus, where we calculated the batch size. But the second one, the cutoff point, was obtained by the optimal value by enumeration. Don't underestimate enumeration. Huh? Normally, of course, in the optimization courses, the OR courses, we don't teach you enumeration. We teach you analytical methods, algorithms, etc. And students, therefore, have the idea that if they are going to construct a proper mathematical model, it must be an LP model, an integer programming model, a stochastic programming model, etc. It's not like that. Sometimes simple models like spreadsheets are extremely powerful and very useful. So this is another point where a spreadsheet model is used to address this problem. The problem is not a very straightforward problem because the complications in costs. You remember the numbers in the influence diagram. All the circles and the shapes were numbered. 8, 9, 7, 12, 10, etc. So the book includes here a number, the length of each cycle. I tried to explain this to you. How do you obtain it? The cycle length, growing phase for duration, plus average flushes per length times the n is the number of flushes, etc. So all the details. I don't know why I scanned this, because you can read it on your own. It's straightforward. So this is how, at the end, the revenue is, the annual mushroom revenue is obtained, and the annual net profit is calculated as annual mushroom revenue plus annual compost revenue is the remaining compost that you do not use can be sold. I think there's some such item in the case. So the money comes from mushroom sales and also from compost revenue, minus the annual tray preparation cost, minus the annual shed cost, minus the annual picking cost, minus annual sorting and packaging cost, annual fixed cost. So all these minuses, when you add up them together, this is the total cost. Okay, so in number 14 of the influence diagram, the annual net profit is computed as total revenue minus total cost in this way. This is the data included, and this is what we do is that the decision variable is n. N is the number of flushes. Okay, you see it here for N. For example, you multiply, anyway, this 28 plus 7N. This is the unknown. We work as if we know this, and we call it N. Okay. So what we do in enumeration, we put N equal to 1 and do all the calculations and compute the profit. Then we put N equal to 2 and repeat, 3 and repeat, 4 and 5. We have 5 different possible values of N to consider. And we enumerate and obtain these results. Flushes per cycle, if N is equal to 1, the total output per year will be this. If N is equal to 2, the total output will be that, etc. As you can see, the maximum output can be obtained with 3 flushes. It's not automatically clear that this is also the number of flushes which provide the maximum profit. This is just the output yet. Sometimes the output can be less and your profits can be more because of the cost and revenue balance. Do you understand this? Do you have maximum output when your output is, do you have always maximum profit when your output is maximum? Obviously not. Okay. Currently, they have been using 5 flushes. This is the blue information. It's about the current situation. And the total output is 7 million kilograms, 7 million. It's a large operation, as you can see. 7 milyon kilo. Mushroom elde ediyorlar. So reducing the number of flushes will at least increase the total production. Now again, there's a lengthy, I explained this case in different ways throughout the years and the material has accumulated. I have shown you the table. Now there is this, each cost item is also summarized here from the book. There's somebody called Brun, Brun's section. He's the manager, Monsieur Brun, who is responsible for compost preparation. So the cost items are, as you can see, mentioned here. 5 million, nearly 5.5 million euros are spent for raw materials, which are straw, manure, peat, casing sand, sterilization agents, etc. And it is black, so it is relevant. Now, this is 123,000 euros are paid as depreciation on yard vehicles and equipment. They are in red, which means they are irrelevant for the project, etc. So this is, again, a complete list of all the... don't be lazy, please, and read these lists. I mean, not for passing this course. I'm not going to ask you about these lists, but to see how many different types of cost items will occur in an operation like this. It is very good for your professional understanding. Many, many different types of cost items. It's a very realistic and very nice case. I like the cases of the book. Yeah. You can read these on your own. For example, some items are both black and red. This one, 5,000 so much euros for truck maintenance and repairs. This is relevant, but 37,000 for depreciation on trucks is irrelevant. Maintenance and repairs is like the wear and tear cost I told you about. Wear and tear is important, though depreciation is not. There are other costs. Most of these are irrelevant. They are in red, as you can see, but some of them are relevant. So, for example, about emeklilik, pension, insurance, which are relevant. Just see why a pension cost should be relevant for this project. It's not a small cost, nearly 500,000 euros. So you can study this. This is the final table which summarizes the findings of the study. As you can see now, this is the difference in profit that the number of flushes will produce. If we take only one flush per cycle, our current profits will be reduced by this much. 0 at the end is our current situation. When we take 5 cycles, the difference is 0. This is the difference in profits, or net additional profits. Okay, as you can see, it is greatest for 3 flushes. It's almost 1 million euros, which is a lot of money. So you see, a cost study like this is capable of bringing you an additional income of 1 million euros, a huge amount of money for this operation. Okay? As I told you, the idea, so growing 3 flushes per cycle instead of 5 provides higher profits as well as a 10% increase in output. It increases both profits and output. This is effectively equivalent to acquiring 7 additional sheds. You know, the other alternatives were making investments to acquire new sheds, or put 2-layered sheds, etc. But the result of this phase of the study has indicated that it's effectively equivalent to acquiring 7 additional. So it seems that the other options can wait, can be ignored for the time being. So this is how we interpret the results. So that's the end of our cost chapter. And next week we start with soft systems thinking, which is chapter